Nope. All right. So we just finished up talking about energy diagrams and activation energy and everything associated with those. And now we're going to move on to something called entropy. But before we get into what entropy is and how it affects chemical reactions, I'm going to go all the way back to Newton's first law of thermodynamics, which tells us that energy cannot be created or destroyed, it can only change forms. Okay? Energy can never be created, cannot be destroyed, but it can change forms. So what does that have to do with this thing I'm calling entropy? Well, let's talk about the fact about what entropy is and how that relates to Newton's first law. So because energy cannot be created or destroyed, the energy within a system that's continually, there is energy, within a system that's continually changing forms, there is a certain measure of disorder that will exist within any system, okay? That measure of disorder is called entropy. So entropy is defined as a measure of the disorder that exists in any system, okay? I'm gonna write it up here. So entropy is defined as a measure of the disorder that exists in any system. Oops. Okay, and we call that delta S. Now let's see if we can understand a little bit more about disorder and how that disorder affects chemical reactions. Let's start by talking first a little bit about entropy in general. We'll look at entropy in different phases. So the solid state of any substance has the least amount of entropy that's associated with it. And if you think about that, hopefully that will make sense to you. Molecules only vibrate. Remember, they're not freely moving in the solid state. They're interlocked together and they vibrate. So because the molecules themselves are not free moving, okay, it has an overall lesser amount of disorder that's associated with it. When we move from, so that's solid. Okay, now we move to the liquid phase. Let's think for a minute about the behavior of molecules in the liquid phase, right? They are freely moving. They have the ability to slide past each other. Because of that, because of the fact that they are able to move independently of each other and they're not locked into their motion by simple vibrations, there's going to be a greater amount of entropy that's associated with molecules in the liquid phase, okay? There's a greater energy also associated with molecules in the liquid phase. And then we can go to the gas phase. And we know that in the gaseous phase, that molecules are actually like pinging off the container and off of each other potentially. So that would tell us that there is the greatest amount of disorder that's associated with molecules that are in the gaseous phase. Okay, this is a logical result when you look at what's going on at the molecules themselves in those phases. So when we look at entropy, okay, entropy increases as we move, disorder increases as we move from the solid to the liquid to the gaseous phase, okay? Okay, so, so two characteristics, two ways to identify an increase in entropy. Okay, so we can identify an increase in entropy in two different ways. An increase in entropy will happen if we have a change in phase in this order. A change in phase going from solid to liquid or liquid to gas, or even solid to gas, or a change in temperature. Okay, and hopefully the change in temperature also makes sense. When we have a change in temperature, I'm going to change this actually, not just a change in temperature, but an increase, sorry. When we have an increase in temperature, we're adding heat, which means we're adding energy, which means we're basically adding disorder to the system. Okay? And if we add enough of that disorder, we'll go from solid to liquid or liquid to gas, right? So all of that should make sense in terms of increasing or attributing to a greater level of entropy. This takes us to the second law of thermodynamics. Now, The second law of thermodynamics tells us that the entropy of the universe has to always stay the same or increase. It can never decrease. I'm going to say that again. The second law of thermodynamics tells us that the entropy of the universe has to either stay the same or increase. It can never decrease. Now when you have, and then we write that like this, we write delta S of the universe is greater than 0. Okay? When we go to quantify or to try to identify whether something is following the second law of thermodynamics, then what we do is we're going to look at the number of molecules that exist in each side of the reaction, and also the phase that they're in. So I'm going to take a break and come back and I'll do a problem like that and explain that a little bit more.